Hi there, everyone. Thank you so much for joining in, and sorry for the little delay that we had here. Basically, we had some technical glitch in the backdrop, and you all know the demo gods need to be pleased all the times, and unfortunately, they were not at our side for the last few minutes. But as they say, better late than never. We are back live, and I can see a few of you joining in the webinar as well. So, welcome to the latest installment in our AI Explore webinar series, and I'm excited to be back here again. I'm Atul. For those of you who don't know, I am a senior developer advocate at InfraCloud Technologies, where I help individuals and organizations adopt open source technologies, tools, and platforms. I'm also a CNCF ambassador, and I organize community meetups in my city here in Hyderabad, India. Now, for those who have been with us on this journey, we have covered quite a bit of ground already. So we started exploring by showing you how we set up our AI lab in the first webinar. And then we moved into the critical area of observability, how we deployed observability in our AI systems. And our third session, we tackled the challenges of taking models to production. And more recently, we talked about architectural patterns for modern AI systems. In today's webinar, our focus is on infrastructure economics, where we would be looking into some technical strategies for cost effective AI scaling. Uh, Being a food blogger, I always have a food reference whenever I'm talking about anything technical. You can watch all our previous videos to get a hang of it. And here's the QR code. You can scan this QR code and get to our YouTube page that will list all the previous videos that we have done on AI Explore. So, being from Hyderabad, one of the most famous dish that we have here in Hyderabad is the Hyderabadi biryani. And to the art of making biryani is exquisite. It's a craft that not many excel at. And while you are preparing a biryani, right, when you want to make a perfect biryani, you first start with the finest ingredients and you prepare your kitchen setup. It's similar to setting up your AI lab. And then you carefully monitor the entire process of applying dum and then ensuring that the meat is properly cooked with the rice and the perfect aroma that comes in. And this entire process reminds me exactly of how you set up AI labs, right? So when you have a AI system that's running locally or maybe in a closed network where a few of your team members are trying it, but when you want to take it to a larger scale, this is exactly how it will be. It's about scaling that Hyderabadi biryani recipe from a family dinner to a restaurant operations. There are a lot of things involved here. You need to balance the quality of ingredients while managing the cost. You need to optimize the cooking process and also, take care of the entire operations and ensure that there's no wastage. So what works in a small scale experiment, whether it's biryani or your AI setup, it often becomes expensive at scale. And that's what we are going to discuss today. And like every time, I am not alone here. I have two guests on these webinar. I have Philip, who is a developer advocate at Baseten, and I also have Aman, who is the principal engineer at InfraCloud. Hey, Philip and Aman, thank you so much for joining in on today's webinar.
Thanks for having me this morning.
Great stuff. Great. So, there is a ritual that we follow on this webinar, and that's basically that instead of me introducing the guest, I always ensure that the guests introduce themselves so that I don't miss out on something that they want to say. So why don't you go ahead and introduce yourself? Tell us what do you do, where are you from, what are your interests, and what do you do outside of work? So, Philip, would you like to go first?
Sure, thanks. So, hey everyone, I'm Philip. I'm calling in from San Francisco this morning. I work at a company called Baseten, which is the AI inference platform for serving high volume mission critical workloads in production. And I lead the developer advocacy team here. So I've been with the company for over 3 years, working across content, documentation, code, demos, all that fun stuff, and including webinars. And let's see, outside of work, I'm a big martial arts guy. I like to train in jiu-jitsu and kickboxing. And I live in Redwood City, which is a short Caltrain ride away from downtown SF.
Interesting. Thanks so much, Philip, for that wonderful introduction. Aman, over to you.
Hey everybody, I'm Aman. I'm based in Pune and I'm principal engineer at InfraCloud. I'm doing this cloud native work from last 10 years now. I've been part of InfraCloud from last 6 years. I've seen and love to work on the complex distributed systems quite a lot. And from last 2 years, it has been more around AI, applying same principles and wherever we can use it. Outside of work, I love book reading and just watching Netflix.
Thanks so much, Aman. So, we have a pretty diverse panel here, whether it's about talking about models and inferences or talking about reading books, Netflix, and martial arts. And for those of you who don't know, a little backstory, I met Philip at KubeCon in Paris, if I'm not wrong. And apart from, discussing about the webinar and AI, one thing we connected on was IPL. And Philip supported Chennai Super Kings, Thala, for a reason. And it's good to be back. We were just speaking on the backstage talking about, how CSK has been performing. So it's quite interesting that, IPL has reached a lot of places. And for all of you who are joining in, please let me know where are you joining in from, what do you do in the comments, and, make it as interesting as possible. So with that, I think it's time to get into the core discussion for today. We have set the stage perfectly in terms of the entire analogy between biryani and AI models and how it eventually scales. So with that stage set up, I'm quite curious always, especially when it comes to AI and infrastructure. And when you look at AI infrastructure, as when you are working with a lot of compute that you need, or a lot of other resources for deploying your models, what's usually the first thing that you spot and say that, hey, this is where I'm spending too much? So Philip, over to you. What is that one or two areas that you always look at and say that, hey, there's something that can be improved?
Yeah, when I think about improving cost characteristics for AI infrastructure, it generally comes down to two things. One is, the infrastructure itself. Are we provisioning our resources correctly? Are we, scaling appropriately with traffic and demand? But I think, honestly, the bigger one often comes more down to model performance. If we can take the same hardware resources and get more tokens, more images, more transcription, more of whatever we're trying to do out of these resources, then we're able to scale more efficiently and have a lower marginal cost of each generation. So, building a cost-effective infrastructure, it is really a combination between both the hardware management and traditional infrastructure domain, and also the research-oriented model performance domain.
Absolutely. I think it's a marriage of two things, and only when both of them complement each other, I think that's when we get the perfect recipe. And like you rightly said, you need to plan your capacity in such a way, depending on the workloads that you have, and also look at not only the infrastructure side of things, but even the model aspects of it. And I think one approach where which at least I have heard when I've interacted with few organizations is taking a different approach. A lot of times companies or organizations would want to stick to on-prem, but there are times when they move into hybrid. And I think that's where I would want to get Aman to share his insights, since he has been quite actively involved in those kind of discussions, especially with multi-cloud and hybrid. So, Aman, your thoughts on this aspect?
Sure. So I think when it comes to multi-cloud or hybrid approaches, all this starts from the fact that what the business is going to serve. Are there any compliance requirements? Can you put the data on the hyperscalers? Can you put on any other niche providers? But there are two things that needs to be answered, like what you are trying to build and what is the limitation, like are there any compliance, anything. Now, Why this approach of multi-cloud has been more popular is because with the advent of these AI solutions, everyone is trying to create some wrappers abstractions around it. So we see one side the foundational models coming out every day, and then the other is how to make them usable. So you might see that somewhere AWS might be releasing 10 different services. It might be good at instances, something, but there are niche providers that are creating solutions on top of these solutions. So be it image generation service, transcription, summarization services. So but you don't have to do that heavy toll of designing the solutions because LLM models is one thing, and then making them consumable is another piece. You have to address multi-tenancy, observability, tracking, request batching, and all those stuff. So there are a lot of things. So that's where this approach of identifying which solutions solves your problem best, considering the factor that it handles your scale, it handles your compliance requirements and everything. So that's where you can leverage. Somewhere some might be cost effective, some might be solution effective. So that's where companies can take the advantage of this. And the other is again coming to the solution, you might be doing something which is more of like a very it doesn't need a lot of data to make an inference, and then you can just push it out to the edge devices because all this conversation and everything, the classic example of how Apple added like the intelligence to the mobiles, right? It can do many smart things even in your device. So why? Because you don't need to push every data out of it. It costs you it costs you actually because it's an egress traffic and egress ingress both are mostly charged in all the cloud providers some rate. So that's where you can save costs. You can bring more efficiency on the throughputs if you deploy your solutions closer to the user on the edge.
Interesting. I think I like the way you put the entire thing around, services that the cloud providers can offer, and also the scale, that they can handle. I think these two are rightly good areas which organizations should, definitely understand before they make the switch or decide, where to move on. Now, I think when we are discussing about, cost, especially when it is, talking about infrastructure, I think the pricing model or cost attribution and budgeting also plays a vital role. And I think I would want Philip to talk a little more about how are the various aspects that are going to affect the overall cost when it comes to choosing a cost attribution model.
Yeah. Actually, if I could just touch on multi-cloud really quick.
Sure.
Because this is something that we've learned a lot about at Baseten. Baseten sits on top of currently 7 different public cloud providers, with more coming, very frequently. And one thing that you really have to be aware of when you're building a multi-cloud solution is that GPUs and cloud providers are like not necessarily fungible in the way that you would expect them to be. An early example that I ran into when I was doing, some benchmarking work a couple years ago was learning that like PCIe and SXM connectors for like A100 and H100 GPUs actually make a huge difference. Not only is the connection different, but actually the hardware behind that connector is different. These are 2 entirely different SKUs where the PCIe's are having lower compute and memory bandwidth than the SXM versions. And then even once you're making sure that you're using entirely, say, SXM GPUs, you still have things to consider in the networking hardware. So, for example, we've recently launched multi-node inference, which lets you use more than 8 GPUs to run extremely large models like DeepSeek R1. And there's actually a lot of different standards on the market for this node-to-node connectivity. So NVIDIA has InfiniBand, which is their sort of standard version of this, which is a pretty high throughput connection, but not every cloud provider uses that. Some have their own custom versions, which can be the same performance, better performance, or worse performance in real world situations. So, building these kind of multi-cloud approaches, especially once you step outside the main CSPs into the broader world of cloud providers, you have to be very careful to make sure that you know exactly what you're getting from a hardware perspective, both on the GPU and on the networking equipment, because otherwise you might make some, pretty fair assumptions about what you're expecting the setup to look like, and actually have to build some kind of abstraction to, cover for the fact that all this stuff works differently.
Absolutely. I think I'll totally echo the whole part where you emphasized on the network bandwidth as well, because we remember, in one of our previous webinars, we discussed the InfiniBand coming in, and then the focus entirely was on the way the models perform and the network bandwidth that is required to either splice, or the way you are probably training your models, or during inference. And like Aman spoke about abstractions. I think that becomes very critical, because the more abstractions that you add on top of whatever the low level architecture you have, essentially that's going to affect the overall performance as well, and that eventually will be a part of the added cost. So yeah, I think that was a very valid point on the infrastructure and the multi-cloud side of things. And let me get back to the model costing sort of discussions. Since we were trying to touch upon that, and I remember you were talking about the per request model, and I think you would be the right person to tell us more about it, because I'm relatively new to the costing aspects of models.
Sure. So the breakdown here is shared inference endpoints versus dedicated deployments. Shared inference endpoints are where you're on a multi-tenant system, which is generally run by some inference provider or a foundation model lab. And the most famous example of this is, of course, going to be the OpenAI like GPT API. So with the GPT API, you and everyone else all send your traffic to the same endpoint. You pay per token of input and output, and you can choose which model you use. You don't really have to manage anything. You don't have to set anything up. This is really great for getting started and small scale projects, because you have absolutely zero overhead. You're just consuming token by token. And that makes your costs very predictable if you know how many tokens you're going to generate, because you're just doing a small project. And it also keeps overhead very minimal. The issue is, as you scale, you start to run into a lot of problems with these shared inference endpoints. One big problem is around rate limits and capacity limits, as well as noisy neighbors causing SLA degradations, high latency spikes, as well as even outages. If you look at most shared inference endpoints, you're not going to see more than a couple nines of uptime. So the other option is dedicated deployments. And for very large scale deployments where you're serving massive production traffic, dedicated deployments can be a much better solution. You get more predictable pricing because you're just paying for the underlying GPU resources. And then from there, as we started this discussion by talking about, it's all up to your model performance efforts, how much you get out of that. So if you can stand up a high throughput, low latency model server on dedicated deployments, and you have sufficient production traffic, then on a per request or per token basis, you're saving a lot of money. To use your metaphor around making biryani, it's like the difference between buying your chicken and rice at the grocery store or buying it at a restaurant wholesaler.
You absolutely nailed that with that analogy. And I think it's very comparable to the entire aspect of reserved versus dedicated instance. Where especially in the yesteryears, or even today, when we all move for the compute, right? A lot of times, if your usage is predictable, you probably go in for a longer run and get a reserved instance as well. Now, I think we have fairly touched upon the larger aspect of costs which are involved on the infrastructure side of things. I think we'll get a little bit deeper into what Philip, you actually spoke about. That it's not always entirely the infrastructure. There's also a lot of emphasis that needs to be put on the the way you select the models, or the way you optimize the performance, right? So I'll get back to you and help us, including me and our viewers, understand how to choose a particular model, or what are the decisions, or what are the factors that affect your decision, which eventually affect the cost when you are choosing the models.
Yeah, absolutely. So my advice is always to start with the largest, most expensive, most capable model you can possibly find. When you are just building an MVP of some product, go ahead and grab GPT 4.5 or Sonnet 3.7, Gemini. The new Gemini 2.5 looks great. And use that, because you're going to be doing such low volume in development that the cost basically doesn't matter. And you want to validate that the thing you're trying to build is even possible. Is there any model in the world that can handle the tasks that you're throwing at it? And if you start there and you're able to build something off of these really high performance models, that's amazing. But from there, you are probably going to want to optimize cost before going into production. So the second step is coming up with really great evals. You have to understand what good quality means for your application. You should have some example prompts and some example responses so that you're able to ensure that any new model you adopt is going to be just as good for your use case. From there, you can start using smaller and smaller models. You can look at some of the Llama models, the Quen models. You can look at potentially, even if you have enough data points in that eval set, even looking into fine tuning. And you should be able to find some smaller specialized model that does a great job. The reason that getting a smaller model, maybe it's a distilled reasoning model, maybe it's a more efficient model like QWQ that's come out recently, an efficient vision model like Gemma 3. The advantage here is that structurally, these smaller models consume fewer resources. You need fewer GPUs and fewer GPU cycles within those GPUs to run these models in production. And so with that, there's no amount of performance optimization in the world that's going to make Llama 70B run as fast as Llama 8B, assuming that you can do all that same stuff to 8B, right? So the smaller the model that you can end up using in production, the better it's going to be for your cost characteristics.
That's an interesting analogy. For someone like me who's completely new, I really, understood the benefit of starting with a really large model, which can do exactly, everything that I wanted to do, and then eventually scaling down in terms of, getting to a smaller models, that smaller and maybe specialized models that can, do the same stuff for me. And like you said, it's very important to have your evaluation parameters in place. So you have your prompts in place, you have your performance metrics, what's exactly required by you, and then you compare which model works, best for you. And I think, at the same time, you also pointed that, as we go down or we choose smaller models, their resource requirements also reduces, right? So whether you talk about compute or whether you talk about GPU, that also affects. Now, taking this discussion to, the other half of the other side of things, where the hardware selection also matters, right? And that's why, Raman, I would want you to tell us, how we could think from a hardware perspective, starting with, instead of how Philip told about, starting from a larger model.
Right. No, but I would like to continue what I think Philip mentioned. It's a great example that when you're starting on validating your idea, it's always best to get to the best of the best and then validate your idea and then come to the optimization part. And that same applies for the hardware selection because there are different categories of hardware. So you have CPUs, you have GPUs, and then they are accelerators, literally created by hyperscalers or NVIDIA, right? Which can even go to the massive scales. But what you need to understand is what you have validated your idea, where it fits in. It can be like a smaller model, district model that you wanted to use, and that does only a very small job. Then there are many optimization libraries that can put it into CPU as well. So you really don't even need a big GPU costing and then management of it and all those things, right? But if that doesn't happen, then go to the GPUs and then again understand your workload. Are you doing just a single request batching? Are you doing do like 100 requests at a time? What kind of users you have? And based on that, choose your models effectively. You could have dedicated instance, shared model, and whatnot. Same that we covered earlier. But that decides what kind of infra you're actually going to use. It could be your own on-prem systems or it could be a cloud-based solution. If you ended up using, let's say, an image subscription service, right? Image generation service, which is already provided by many providers. And your valid idea, prompting ideas and everything works fine with it, right? Then why do you have to really own it? If the cost, your economics comes into that you can still make profit out of. So that's where you land up with your business, your ideas, and then you validate it. And then you incrementally go to the choice of hardwares. You can start with scale out architectures, just start small. And then when you feel that it is increasing, you're getting massive amounts, you apply the same strategies that we talked earlier at the start, that you can have auto scaling, you can then do the right sizing and all this stuff. But you don't need to like jump with the H200, H100, that these are the best in the market. I will only use those.
Interesting. That's quite a, different, rather similar POV, on how to get started. And I think once you have decided, the models that you need, or the infrastructure that you need for your requirements, that's when I think the actual optimization start. And Philip, you correctly mentioned, there's no dearth of optimization available which can bring down a 70B to an 8B performance, right? So let us quickly touch upon some optimization techniques when it comes to serving. I think there are a few points on the screen, but Philip, anything that you would like to add to these, or maybe reiterate?
Sure. So I actually just gave a talk on this at NVIDIA GTC last week on how to use TensorRT LLM in particular to implement a bunch of these serving optimizations. And that was a 40-minute talk, so I'm going to try not to say everything I said there right here in this webinar. But I would definitely encourage anyone who's interested to go give it a watch once it gets posted within a couple days on the session catalog. Anyway, looking at some of these optimizations here, one thing is that GPUs fundamentally are throughput machines. They are really good at batch workloads. And when we think about model serving, at least in the next token generation step, generally we are bound on memory bandwidth. So how quickly can we read things out of VRAM? That's going to be the bottleneck on how quickly we can generate tokens. We want to approach being compute bound as much as possible. We want to eliminate the memory bandwidth as a bottleneck. And one way to do that is batching. As we increase our batch size, we do use marginally more memory as that batch size increases, but we use substantially more compute. So less of our compute cycles are going wasted. In terms of, the caching strategies, this actually, goes back to request routing as well. So, that large batch is going to help with our throughput, but what about our latency? So one great thing for that is something called KV cache reuse. As we, run model inference, we are generating, we're reading the weights, we're reading the activations, we're also generating the KV cache, which is the result of each computation. So especially for prefill, which is that process of generating the first token, we are going to be able to, if the prompt is, say, a repeated standard prompt and then a small user thing at the end, or maybe it's shared context like an entire code base going in and a quick little summary from the user at the end, we're going to be able to reuse the computation that we did originally in order to basically skip a bunch of prefill work and go directly to what's novel about this request versus the last one we got. That's where routing comes in, because we don't necessarily want to put our KV cache on every single GPU in our distributed system. That would take a ton of memory. And we can use some strategies like offloading KV cache to CPU, especially on Grace Hopper type architectures, where you're able to have a very high bandwidth interconnect between CPU and GPU. Or even if you have fast enough memory disk, you could maybe even keep some KV cache there. But another option is to just limit KV cache to different, different GPUs within your model serving architecture. If each one has certain requests cached, and you can use request routing to route similar requests to models that potentially already have the relevant KV cache information, then you don't need to duplicate your cache everywhere, and you're still able to get a very high hit rate, which is going to, of course, improve latency and throughput, reducing cost.
Wow, that's quite a really high energy, high octane capsule that you gave us of your 40-minute talk. And I think that was quite interesting, and to understand the batching process and how the KV caching can be used for this, and eventually routing, and a mix of all these three can actually affect the functioning or the performance. And like Philip said, that this was more of a large talk that he gave at GTC. But if you all are interested to hear it more, and maybe us doing some more interesting things around this, let us know in the comments. Maybe I'll try to lure Philip in with a biryani, and we could do another interesting webinar focusing just on the optimization techniques. And before I move forward, there is one question that I've been sent by my team here, and I don't know how I feel it's we are at the right juncture to answer this, and I think Aman, Philip, any one of you could take this. And the question is, how do you decide when to use CPU versus GPU for inference scaling? And are there any clear cost performance benchmarks that you have when you need to decide it? And any one of you can take this.
Sure. So I think CPUs are really good if you are doing something which is like a lightweight model. Because like just Philip was mentioning about this memory cycle, this computational overload and all, right? So you cannot fit like a too big model or a too big request within the CPU, right? Because the way it is designed, right? It doesn't have that much of a bigger memories that it can just push it back and then read it from there. So that's where if you have like a low, like a very small size models, you can expect low latencies, and you can just put it onto the edge. That's a good case for that, right? Because that's easier, that's available everywhere. Any user can acquire those hardwares. But when it comes to the performance systems, when you're targeting about high scale volume, your model is going to be big. With volume, you might even move to the like bigger size models, and then you come into the cycle of I think Philip was mentioning about optimizations on the usage of memory, and that's where you need really the good GPUs and the accelerator hardwares, and that is usually how you can make a decision. But
Interesting. Philip, anything else would you want to add to this?
Yeah, just that like I don't really ever think about CPU versus GPU, with the exception of like some local embedding model inference. When I think about production workloads for basically any of the models that I run across in my daily work, it's entirely CPU. The decision is more like, which CPU is this in? H100, should I, use an H100 multi-instance GPU to, save on cost for smaller models? Can I fit this on an L4 and still get good performance? Those are more the trade-offs that we're generally thinking about.
Absolutely. I think when you are operating at scale and especially in production, I think the whole CPU part takes a backseat, and that's when you ensure or try to at least ensure whether it works with the latest GPUs or the hardware that you have. Now, moving on into our discussion, I think we spoke about infrastructure cost at the beginning. We spoke about the various opportunities when it comes to multi-cloud or hybrid, talking about the costing attributes. We then dived into the whole optimizations part of it, and I think logically it makes sense now to talk about the operational efficiency, because logically, when we have optimized the system as much as possible, we have optimized the models, and now it's all about efficiency, and how do we improve that. Now, to initially talk about things, a lot of existing practices are still valid when we are working with AI workloads. Talk about DevOps or MLOps, and there are a lot of different attributes that are taken care of, especially when it comes from a cost point of view. And there are a lot of advancements and newer techniques, newer way of working that's coming in. So, Aman, would you like to shed some light on the DevOps practices which actually help for inferences?
sure. So in the last 10 years, with all this containerization and distributed systems, what we have done on the DevOps practices is more like creating a generalized set of practice that accelerates your production time. Like you get to this, your software development life cycle, entire life cycle reduces. You get more effective, you produce faster, you get to more visible results and all. And those fundamental remain same even when you start using these AI systems. Reason being, you're not using AI systems for fun. That's completely different than you don't need any operational practices. But if you're using it for business, you need to use it like a machine. Like every day, day in, day out, different developers will be working on it. So you need pipelines. You need to have same systems as you used to do your software development. There could be changes in the pieces or components that might be in the pipelines, but ultimately you need that whenever you make a change in the product, it should be released, tested, validated, and customers are using it. When it is out in the production, you're tracking its complete observability. You know where the things are going, how GPU is performing, how your machines are performing. Because whatever we're talking about cost, those decisions can only be made when you have these observability metrics. One way is you just go in and look at the bills, but then that will not tell you like what really happened. Did your GPU perform based on your user request, or it was just a heavy costing of the GPU, like we were talking about the dedicated models? So that's where you need all these CI/CD pipelines, infrastructure as a code practices. Environment should come as and when you want. You're detached to the cloud providers for anyone. You can easily move to the different, like earlier Philip was mentioning about there are limitations of different cloud providers and different hardware. So you should be ready to get out of it as easy as possible. Of course, it might not be like 100%, but you should be there at like 80% that your code is automated. And then containerization is something we have been experiencing from last 10 years. It just makes your work easy, make it repeatable, and you can just pass it on between different same practices. I think are getting applied to all the inference models. We are seeing NIM blueprints and all those stuff that are coming out. It's become all easy to get just get a model, deploy it, provide an API endpoint to others, and then people can just rotate it around between the images.
Absolutely. Philip, anything you want to add? Something that you are being part of, your team is doing, which you think could be a good practice for everyone else?
Yeah, I mean, I think Aman nailed it. Like, one thing that we've shipped recently that's had a big impact is customized environments. You want to make sure that you're able to have the same development, staging, production loop that you experience for everything else in your product within your models as well. These ML models, they're now mission critical systems within people's production applications. And accordingly, they need to be treated the same way as any other mission critical system and integrated into the same sort of monitoring and observability tools like Grafana that you might be using for other components as well.
Yes, I think the whole aspect that fundamentally the practices remain the same, and it's most important in production or your entire processes that your each environment actually is mirror of the production, so that you are able to test it, develop it in the exact same setup that you have that your customers are using. And I think Aman touched upon the observability part of it, and I think one of the key things over there is cost monitoring and optimization. So what are some key metrics, Philip, if you would want to add for tracking various costs that are associated when you move to production?
Yeah, I mean, I think the most important thing is just making sure that you're keeping track of your GPU spend. Like, GPU spend is going to be the vast majority of this entire cost here. I think that, setting limits to your scaling so that you're not going to scale past a certain number of replicas is important. And to make sure that you have good loading, actually more around traffic spikes, that kind of stuff, because that's what's going to inform cost. So making sure that you're able to understand when you're scaling up, why, and that, scaling up is the right decision in these cases. That's going to be what's going to keep your cost under control.
Absolutely. You don't want to be running something and then just forgetting about it, waking up next day to see your credit card being charged few $1,000s because something was just running and you never paid attention to it. And I think one of the ways of doing that is also sharing resources. And I think it's inevitable to do that with the current cloud native landscape that we have. So this one's again for both of you, Philip and Aman. What are various techniques that you see where we can implement resource sharing and improve the performance? Philip, would you like to go first?
Sure. So, obviously, if you're using a shared inference endpoint that you're not running yourself, then resource sharing is very easy. Everything's multi-tenant out of the box, and you don't really have to worry about this. Once you move to dedicated deployments and you're building this infrastructure yourself, one thing that's really critical is being able to scale down to zero. So if you're not sending traffic to a model, there's no GPU running, you're not spending any money. Scaling to zero it's a bit of a tricky challenge because you have zero as kind of like an edge case in the number of resources to have in your system. And another main challenge in scale to zero is what happens afterward. What happens when you get a request? How do you enqueue that request in your system? And then most importantly, have a really fast cold start where you're able to go get a GPU on a sort of on-demand basis. You're able to load your container and your model weights into that GPU, spin up the model server, get that started, take that request out of the queue, handle it, and send it back to the customer. This can be a really slow process, actually.
Right.
We're talking about minutes or even hours if you don't have an optimized system here of just like waiting for a GPU on whatever cloud provider and then loading, gigabytes or hundreds of gigabytes of model weights on. But with the right optimizations, with making sure that you have a warm pool of GPUs to pull from, making sure that you have your weights and your containers cached very, very close to these GPUs, you can actually reduce these substantially. So, for example, we've seen cold start times of like 2 minutes for DeepSeek R1, which is a 671 billion parameter model, which means 671 gigabytes of weights alone are getting streamed in that time. So there is a lot that you can do on the infrastructure side to make these cold starts very, very fast.
Interesting. I think you simplified the entire process very much. I'm sure there are a lot more moving parts, to ensuring the cold starts are reduced as much as possible. Aman, anything from your end on this?
I think Philip pretty much covered it. I think I only covered the last point. Like we have already seen this in the systems like API Gateway, or if you have worked with like data lakes warehouse, you always get what you pay for. And where so there is a prioritization mechanism, and similar principles apply to this. You might have seen like if you're using a free version, your request will be like we can only do 30 requests, and then you will be shifted to a lower model. So similarly, understand what kind of workloads you are serving to, what kind of customers you're serving to, and based on that, do an intelligent tiering. You don't have to like put everything for everyone. And understand what layer you are at, and if you can add those API gateway layers or like request routing layers where you can just understand, is it a priority request? Is it a delayed request that can happen delayed? So that kind of routing can really help you handle your resources well.
Interesting. And I think one of our viewers sent in a question just at the right time when we were talking about resource sharing. And I think it's a fundamental question, but then it's a very practical question. And it's about so the person's asking, would it not be difficult to monitor the resources when they are shared across different models? So how do you actually track your resources when they are across different servers, or when you're sharing it across models?
I think Aman should take this one. I honestly have no idea because Baseten handles this for me.
Yeah. So again, like I said, same fundamentals apply here because when you run like a node, still that node, if you're running 10 containers on it, those 10 containers are literally sharing those node. So you have to understand the system in the same analogy that if you're running a GPU server, that's a server literally. It's not like literally an AI-enabled thing. It's a GPU server at the end, right? So if you're putting 10 processes on top of it and those are utilizing your GPU, then you have to track those process usage and how are they being utilized. And then you come to a conclusion that really is the wise sharing that is happening. That is what you were anticipating, that these 10 processes are same, or 5 processes were literally something that are on free tier that can be delayed or can be shifted to lower instances. Then that's kind of routing that comes out of your observability stack. So treat it same because it's just the same systems. It's just the new softwares and new product that are coming on top of it.
Thanks, Aman. I think that answers your question when it comes to monitoring the resources. And yeah, I think we have pretty much touched upon the surface, scratched the surface of cost when it comes to infrastructure, to model performance, and eventually on the operational efficiency. And I think it's the right time to hand over to Philip to talk more about what Baseten is. I know they are doing a lot of interesting things around inferences and improving developer workflows. But then I will hand it over to Philip to tell us more on what the offering is and how it can help us on the scaling side of things.
Thank you. So Baseten is, as I said in my introduction, it's a model inference platform for serving mission critical workloads in production. And our customers are top AI native companies who are building, tools and applications powered by generative models. When we look at, AI applications, I got one slide ahead of myself. When we look at like the path to production, generally you start in a sort of alpha with this shared endpoint multi-tenant system that we've been talking about, where you're just making individual requests to the models as you try to build out your service. But eventually it's time to launch that service. And in that case, you start thinking about scale. How do I first get to a dedicated node where I'm able to, serve this model without throughput limitations? Then as I get more users, how do I scale that node up so that I can have multiple nodes and fluctuate based on traffic? You also might want to scale that across multiple regions so that your models are close to your user for low latency and you're able to access more resources. And then eventually across multiple clouds so that you can do a bunch of these cost optimization strategies that we've talked about today. The problem is this is really complicated. So, as your users are coming into your application, you've got a model performance problem in terms of making sure that you have all of these different optimizations implemented. You have infrastructure problems around routing, networking, multi-cluster management, as well as hardware issues, like how are you able to select and provision the hardware you need? How are you able to get it on demand? And all of this stuff relates to each other. So it's not just a series of linear issues to solve. Every single issue affects the other issue. For example, which hardware you use affects, which model performance optimizations are available to you, as well as which clouds and which regions you're able to access. And inference is at the root of every single trade-off you're going to make during this process because you're trading off between performance, quality, and cost in every single decision you're making here. What Baseten does is it provides the model performance tooling, the scalable infrastructure, the embedded AI engineering expertise, and the cloud-native infrastructure to help you scale throughout this entire journey, going from that single node to the multi-node, the multiple regions, the multiple clouds as you serve your compound AI workloads in production. So what does that actually mean? Like, what does performance-grade inference infrastructure look like? Well, you have to have excellent performance with support for every framework. TensorRT LLM is super great, but maybe doesn't support every model. You might also want something like SGLang or VLLM for certain models. You need the scalability to both auto-scale from zero with fast cold starts like we talked about, as well as scaling up to handle, as many as billions of requests. You need massive uptime across every cloud and every region with minimal lock-in so that you can add, whatever complexity you need on your end. And then, of course, cost efficiency so that you're able to, optimize for cost while still making sure you hit your latency SLAs and maximize the utilization of GPUs as well as spend down any cloud commits. That's what Baseten does. So we're powering leading AI companies who are building some of the best, tools today for using AI models in both a B2B and B2C context. And our actual platform is all about developer experience. So we're trying to make it easy to optimize, package, and deploy models, build compound AI systems out of multiple models, run those systems anywhere, and do that, with a pretty fun workflow that, doesn't really that doesn't stand in your way of getting to production, and in fact helps you get to market sooner. So what does that actually look like? You can come onto Baseten and you can come into a model library and grab a prepackaged model, or you can take any open source fine-tuned and custom model and package it yourself using Trust, which is our open source model packaging framework. So once you select a model, you deploy it into production. What you get is this dashboard that shows all of your different model deployments. You can say, for example, name your deployments to keep track of them. I could name this one Fred. And you have, information on your instance types. You can select different CPU and GPU instances, H100s, H100 MIGs, all that kind of stuff. You also get some metrics that's showing your inference volume coming in, your response times, that kind of stuff, as well as nice to haves like activity logs and logs for your actual inference requests as they come in. Now, let me show you the auto-scaling component really quickly because that's interesting. So on auto-scaling, and this is on a sort of like per deployment basis, you can configure it. You can scale down to 0. So if you're getting no traffic, your model shuts down and you're not spending any money. And you can scale all the way up to a configurable number of maximum GPUs. Within auto-scaling, there's a few important settings to pay attention to. So the first one's that auto-scaling window. That's the time frame of traffic considered for scaling decisions. So say I'm going to look at my average volume over the last 20 seconds and use that to determine if I need more or fewer GPUs. On top of that, there's also a scale down delay. And that's important because, even with fast cold starts, you don't necessarily want to scale down too aggressively. If you were to, for example, have a traffic spike in a sort of bimodal pattern where there's a huge spike, it backs off for a couple minutes and then spikes again, you might want to just keep the service up through that so you can handle that second spike. That's what that scale down delay lets you do, and you can scale that up to as much as an hour. There's also the concurrency target. That's the number of requests per replica before scaling up. That's an incredibly important number. That's going to be based on the batch size that your model server is able to handle with the performance that you're looking for. So the higher that concurrency target, the fewer replicas you're going to need, but the higher the latency is going to be for each end user. So finding that right balance there is an important model performance question. And within your Baseten dashboard, you can actually see how, as that inference volume and response time scales up and down, your replicas are able to scale up and down in conjunction. So we see the traffic spiking here, the replicas come up with some replicas starting up to handle it. And then as that, scales back down, it comes down. So we're fluctuating between, in this case, to handle this traffic, like 23 and 28 replicas over the last hour. And you can see as replicas scale down and back up in response to traffic, how we have the cold starts on this yellow line here and the active replica counts on this blue line. Traffic-based auto-scaling is definitely the way to do it. There is also an approach around, doing a auto-scaling more based on GPU resource utilization. But we found is that traffic-based is going to give you, better, more predictable scaling, and is going to prevent a whole ton of issues that came out of resource-based scaling. So yeah, that's a super quick lightning round overview of Baseten. You can take any model. That can be an open source model, it can be a custom model, or you could say take one of these open source models and fine tune it and deploy that as well. Optimize it with our engine builder for maximum performance, and deploy it into this system and scale it in production.
Wow, that was pretty interesting. Thanks a lot, Philip, for that quick yet insightful demo. I think the way you explained the auto scaling features that Baseten provides, especially dealing with the scale up and the scale down window, which I feel is pretty simple to look at, but I'm sure there's a lot of brainstorming and decisions that go behind in deciding and arriving at that particular number. And I think for me personally, I'm very much new to this, and I think the way you spoke about focusing more on traffic, like you mentioned, based on your analysis of how users are using your services, that scaling based on request traffic is a better option rather than GPU resources alone. I think that gives you a larger picture, and I completely echo that. So thanks a lot for that insightful demo. And yeah, I think anyone who's seeing this, if you want to try, you can head over to baseten.co and you can try pick up the models from the model library and then see what it is for your use case. And I'm assuming the Baseten team will be available at KubeCon in London next week. Am I correct?
Yes, we will have a booth at KubeCon London. I'm not going to be there personally, but we're going to have a lot of great people out there to help out and, tell people more about Baseten.
Interesting. Yeah. So if you are attending KubeCon in London next week, do visit Baseten's booth. Praise Philip for the wonderful demo that he has given us, and do try to learn more about the exciting offerings that they have. Now, before while I was going through the questions, before I take on any other questions, there's one particular thing which I want to ask both of you before we actually wrap up, and it's more about on the emerging trends. So what are some trends or technologies you think will significantly impact AI inference scaling in the next few years? So Philip, we would like to go first with you.
Sure. So I think like a few big ones. Number one is open source. We've seen with DeepSeek coming out and with the rapid release of subsequent, reasoning models like Quen's model. We're seeing that the gap is not only closing, it's really closed. The new DeepSeek V3, for example, is one of the best non-reasoning models out there that came out a couple days ago. So you now have a lot more choices for what you use for your models in production. Now, from there, like the other trend that is just as important here is these open models are not only coming out and getting better, but they're getting smaller for the same performance. So if you were to take this is kind of back to what I was talking about at the beginning, where if you're building a prototype, you should just use the best model. And one of the great things is that if you just use the best model and you wait about 6 months or 12 months, there's going to be some open source model that's just as good that comes out, and is going to be not only just as good, the just as good one might come out the same month, but it's going to be just as good and a tenth the size, cutting your costs substantially. So for the same level of intelligence, costs just plummet on, the timeline of months or, even a couple years. And then the final thing, around this, that's kind of a counteracting effect is, we are seeing more reasoning models and more use cases around reasoning models. Reasoning models, that's inference time compute scaling. So now inference becomes even more important than training in the amount of quality output you're able to get. Just running the model for longer is getting you higher quality output. Because of that, everything we've talked about today around cost optimization from a performance angle matters even more. And as we see new hardware come out, like the Blackwell GPUs, the B200s, the GB200s, being able to leverage, these larger, higher capacity, higher throughput, more efficient systems is going to be massive for building real-time user experiences on top of these reasoning models.
Interesting. Aman, what are your thoughts on this? What are some trends that you feel will change the way?
Yeah, I think few of the things that we spoke about, like multi-cloud, hybrid approach, and all. So there are trends like how do you take that cost arbitrage benefits, right? How do you do that smarter routing? You can still use all three different cloud providers or major providers, and how do you do that smart routing, context-aware routing? That probably this is best to be routed to this one, and this is handled well there. So that saves money to the business. Then it comes to like we have spoken about it in the earlier webinars as well. Like inference parallelism is a really great option to save or optimize your resources. Philip showed about the scaling part. So that is going to become more and more interesting signals will become. I mean, as we progress into newer hardwares and newer deployment strategies, there will be more signals that can help you do the auto scaling and scale downs because currently, we are doing like more on the performance of the models, but it could be more on the infrastructure side. You can mix those signals, like we have seen in the entire container space. Like we started with normal metrics, then came custom metrics, and then came like you can literally pick up metrics from anywhere in the world. So similar things are going to happen in this space as well. Use more signals to make more intelligent decisions.
Interesting. And to I think some of what both Aman and Philip said, I think one leaf that I would like to take away from this particular discussion on future trends would be basically waiting, because your computational powers are doubling. We talk about Moore's law, but then in the age of AI, there's no harm calling it the hyper Moore's law, because the computation power is just increasing at logarithmic scale, and eventually the models are also improving their performance. So you are now able to achieve the same level of power. We could do it, and at the same time we are getting it at 1/10 of the cost. So I think with that we come to the end of our today's webinar, and I would like to thank Philip for spending his time giving us that really interesting yet short demo. And I'll definitely try my best to get him on again sometime to do something more deep dive. So thanks a lot, Philip, for joining us today.
Thank you for having me. It was great talking to both of you.
Thanks, and thanks a lot, Aman, for always being here with us. It's always great with you around. So yeah, with that, we come to the end of today's webinar. Do scan this QR code on your screen. We come up with more interesting AI webinars in the future. So scan this QR code so that you are notified and reminded of all our future webinars. And once again, thank you for joining us today. I hope you had a really insightful time. It was great learning for me. I'm sure going to go back and watch this recording again and probably reach out to Philip again to help me learn more things. So thank you so much, and have a wonderful day and wonderful evening from wherever you are joining me from. Thank you. Bye bye.
Thank you,
Bye-bye.
everyone.